Chapter 3 is entitled Quadratic Equations and Complex Numbers, and on the page before it, page 91 in our textbook, they have a Maintaining Mathematical Proficiency page talking about simplifying square roots and factoring special products. The page is sitting here before you, and I also pasted it onto the back of a worksheet that I'll have available for you as well. The examples that follow are inspired by this. To simplify a radical means to factor out the greatest perfect square if it's a square root, or the greatest perfect cube if it's a cube root. And so in these three examples, we're asked to do that. When we look at 50, we try to think of the factors. What are some things that go into 50, like 5 and 10? But a better example would be 25 and 2, because 25 is a perfect square. We could break it up as the square root of 25 times 2, but we could also break it up further to say that it's the square root of 25 times the square root of 2. And if we know that the square root of 25 is 5, then we can write our answer as 5 radical 2. If that's true for multiplication, that we can break it apart into two different radicals, the same rule applies when we're talking about division. I'm not sure what 11 divided by 49 equals, but our properties tell us we can break it apart into the square root of 11 divided by the square root of 49. That's going to give us the square root of 11 over 7. And if we want to go further, we can also write that as 1/7 times the square root of 11. In both of these cases, what's left under the radical is either a prime number, or even if it's not, there's not a perfect square still in there. When we look at example 3 here, it's talking about a cube root. I know it says square roots on top, but I just want to take one moment to look at a cube root, and I think it'll help us to understand a little bit more what's going on. 24 and 1,000 are both even numbers, so maybe it would make some sense to say, does 2 go into both of them? Does 4 go into both of them? Does 8? But another way to think about it is that 24 might have a perfect cube in it. 1,000 might have a perfect cube in it. So I'm going to make the suggestion that we start to break things apart. And I recognize that in the denominator, the cube root of 1,000 is like the cube root of 10 cubed. So that helps me to see how we're going to simplify that. 24 has lots of things that multiply into it. And so as we start to consider possibilities, I think of 2 times 12. Okay, great, but neither one of those are a perfect cube. Okay, well, what about 4 times 6? 4 is a perfect square, not a perfect cube. 8 times 3. 8. 8's a perfect cube. Another way of expressing 8 would be 2 cubed, and there's still a 3. So very much like with the square roots, we can do the same thing with cubes. By the way, square roots are so common that we don't see the index. You don't need to put that 2 up there as an index, but it might help us to understand that cube roots are going to have the 3, something to the 4th is going to have a 4. So we proceed. The cube root of 2 cubed is 2. The cube root of 3 cubed, the cube root of 3 will just remain. And we have a 10. Now, if we want to go just one step further, we could say that the 2 and the 10 simplify. So we could write this as the cube root of 3 divided by 5. And if it's preferable, we can take a step similar to in number 2, and we can say that this is 1/5 times the cube root of 3. Another challenge for us in this chapter is going to be to factor, and sometimes there are special factors. And in this Maintaining Mathematical Practice page, they give us differences of squares and perfect square trinomials to try to work with. So I'd like to just take a quick look at differences of squares. When we have something like a squared minus b squared, it factors into a plus b and a minus b. And I would like to just reverse the process real quickly just to see that we are correct here. If we wanted to FOIL this thing, a times a is a squared. The outsides are going to give us minus ab, the insides plus ab, and the last minus b squared. If you see that the outside and the inside terms drop out, we're left with a squared minus b squared. If we take the perfect square trinomial and try to do the same thing, reversing it, when we have a plus b times a plus b, if we FOIL that thing, again, we're going to have our a squared, a times b times a, we can just switch that around alphabetically, and b times b. And so, excuse me, when we merge our outside and inside terms together, we come up with that 2ab. Well, we're going to be factoring, we're going to be undoing that. So let's take a look at these two examples, 4 and 5. We're looking at a squared minus 121. Clearly, a squared is a perfect square. The minus sign tells us that it's the difference, and 11 squared is equal to 121. So that should factor into a minus 11 and a plus 11. Notice up above I had a plus b and a minus b. It doesn't matter whether we have a minus or a plus. The order doesn't particularly matter there. When we come over to the example 5, what we're checking out here is that we have b squared is a perfect square, 16 is a perfect square, and the square root of 16, if we wanted to say 16 was 4 squared, 4 plus 4 is 8. That's 4 times 2. And notice that there was just one a and one b. We could talk about a b there. When we go to factor this, check out what happens if we say b minus 4 times b minus 4. Reverse the process. You know for f we're going to get b squared. For the outsides, minus 4b. For the insides, minus 4b. That's where the minus 8b comes from. And negative 4 times negative 4 is 16. We can write that as b minus 4 squared. And it's not the main focus here, but if we said something like y equals this expression, can you see that we're going to have intercepts at plus or minus 11? And also, if we said y equals over here, do you see that we're in vertex form? And we would have a vertex at 4, 0. Two more examples. First of all, in example 6, it's a binomial, and 9 is 3 squared, and 16 is 4 squared. C squared is c times c. So we're looking at another way of writing this, 3 squared minus 4c all squared. That should break into 3 minus 4c and 3 plus 4c. For example 7, I'd like to look at it two different ways. First, I'm going to take two sets of parentheses and say, let's go with this. And what's going to multiply times itself to give us 4d squared, 2d, and 2d? What's going to multiply to give us 36, meaning by itself, 6 and 6. We want to multiply to get a positive, so our sign should be the same. We want to add to get a positive, so both of these signs should be positives, plus signs. Does that work? We know that the F and the L in FOIL do. If we check out the outsides, we're going to get 12D. If we check out the insides, we're going to get 12D. Add them together, and we should get 24. If you want to factor further, you might notice also that there's 2 and 6, they're both even, 2 and 6. If we take a 2 out of both of these, that would be equivalent to taking out a 4, and we would be left with d plus 3 and d plus 3. Certainly you could bring that together to be 4 times d plus 3 squared. But I'd like to just pause for a second and redo that problem, keeping in mind what we finished up with. Because from the very beginning, we can go with the greatest common factor. 4, 24, and 36 are all divisible by 4. Your life might be much easier if we factored out a 4 and we're left with d squared plus 6d plus 9. Now, when we go about this business, isn't it easier to see that d squared can break up into d and d, 9 can break up into 3 and 3, and going ahead with our signs, don't we come out ultimately to the same answer? Please don't neglect, as we get into some more fancy work here, don't avoid some of the obvious things like greatest common factors. It should make your life a lot easier. This last abstract reasoning question is taken almost directly from the page Maintaining Mathematical Proficiency. It's a little bit of an easier example. It's asking what values of a and c could make this a perfect square trinomial. So when we consider that b equals 6, we want to know what number adds to itself to get us to being 6. 6 divided by 2 equals 3. So we're looking for either a or c to equal 3. So let's go about it this way. What if we had x plus 3 and x plus 3? When we FOILed, just reversing the process, wouldn't the o, the outside terms, give us 3x? And wouldn't the inside terms give us 3x as well? We would have a 9 for c, and we'd have to have, what would be our a value? If we throw a 1 in there, we would be in good shape. So a would equal 1, and c would equal 9. But we should also be able to take the same idea and switch it around. What if we said 3x plus 1 and 3x plus 1? When we O and I this thing, wouldn't we still get 3x plus 3x? If that's the case, then we would be looking at our A equaling 9 and our C equaling 1. There's a worksheet that corresponds to this, and again, if you're interested in seeing what the book has to say, it's page 91 in Big Ideas.